All right, let's continue on this example 5.3. Okay, so previously we talked about we have a population of 960 and we want to collect 60 measurement. So that would be 1 in 16th sample. Okay, so I try to put it into a this format so that you can see it nicely. So if I have 960 population, then I want to choose 60 sample from the population. So in this case, I would have 1 in 16th sample. Okay, so I would arrange the sample from the first up to 16th and then 17th item, etc., all the way up to 960, right? So if I have a random start, let's say a random start is 6, and then the entire row of 6 would be obtained. Okay, and then the second item would be the 6th item plus 16. So that would be the 22nd item and the 38th item, etc., etc. So in this case, this size is equals to 60 of a row of 60 items I would collect it, right? So that would be a one systematic sampling. And once systematic sample is selected, I can calculate one y bar out of these numbers. But in reality, I can't assess the distribution of different y bar because I only collect one sample, right? So that's why after I have collected those sample, I can actually put it into this way so that I'm actually indeed doing 10 times of the systematic sampling. So I'm repeating 10 times. So I have ns equals to 10. If I put it into 10 times, repeated 10 times, then the new size would be 60 divided by 10. So each of the new sample would be having a size of 6. Then the interval, I need to put them further apart. So if I repeat it 10 times, so it would be 60 multiplied to how many times I want to repeat it. So it would be 160. So what I'm trying to do is to arrange the original population data, like from the first all the way down to 160. Then I would have the 161st item, 162nd item, etc. Now, if I randomly have a start, let's say a random start is 6. And if this is the case, since I'm dividing the original 60 samples into 10th of them, so each of the sample would have a size of 6 instead of 60, right? Because I repeated 10 times. So 6 items, I would have one y bar 1, let's say, calculated. And I would have a y2 bar calculated if I have a second random start, and then a third random start, and y3 bar, etc. So now I would have a distribution of the y bar. So that's why we can do the estimator of the variance if we repeat it 10 times. Okay, so this is how we do in this example. Then for that 10 repeated systematic sampling, we can have 10 random starts, and then we collect the data from the populations. So if we have the random start to 6 item, and then the 166th item for the second element selected, so now we would have 10 of the sample means. Then we calculate the means of means using equation 5.5. So means of means, so we add up 10 of the y bar divided by 10s, and then we can obtain the means of means over the y bar. Repeated systematic sample would be the mean estimate, and then we can look at the variance of each of the y bar to the means of means, and we have the sample variance as y bar squared calculated, and substitute into equation 5.6 to find the estimated variance of the y bar. Now, beware, in equation 5.6, as y bar squared is calculated using number of times repeated minus 1 as the denominator. And here we also have ns, number of times that we repeated. But the finite population correction factor, we are still looking at 60 out of 960 in the population. Okay? All right. So we can move on. And just bear in mind, we are indicating the sixth element, or the 166th element in the populations, but indeed the actual numbers we need to calculate. So let's look at example 5.6, a park charge submission by car load rather than by person. So a park official wants to estimate the average number of persons per car for a particular summer holiday. She knows that from the past experience there should be approximately 400 cars entering the park, and she wants to estimate sample 80 of them. To obtain an estimate of the variance, she used repeated systematic sample with 10 samples of 8 car each. So now we are having the total of all of the y bars equals to 41.63, and then we have the total of the y I bar square, which is 177.4110. Okay, so let's say we repeat it with the repeated systematic sampling. We repeated 10 times, and each of the sample we have 8 cars. Okay, so let's say we have the random start second, and then if we repeat it 10 times, so the k pi in this case would be 50. Okay, so the first car we start would be the second, and then every 50 car we would choose that into my sample. So the second car would be the 52nd, and 102nd, 152nd, etc. Okay, so for the first sample, we ask how many passengers in their cars, and then we calculate the average number of passengers for the first sample, which would be 3.75, and then the second random start would be the let's say would be the fifth one. Then every 50th, so the second element in the second sample would be the 55th item to be chosen. Okay, so just bear in mind, in this example, we are calculating the average number of person per car. So we're actually the second, 52nd, 102nd, etc. are the number of car from the populations. Okay, the arrange the number of the car in the population. But what we actually need to look into is how many person. So when we do the calculation, we're actually taking the average of 3, 4, 5, 3, 6, 1, 4, 4, but not 2, 5, 52, 102, 152, etc. So sometimes in the past, students make this kind of mistakes when they calculate the y bar. Okay, so in this case, for one systematic sample, we look at the intervals, because we want to collect 80 samples, so 400 population. So originally the kth interval would be 5. Okay, now we want to repeat it 10 times, so the intervals would be 10 times k, so it would be 50. So first of all, we would have from the first car to the 50th car, we would have 10 random starts. So you can see the random start to the second, the fifth, the 7th, 13th, they are chosen from between the first and the 50th. Okay. Suppose the following 10 random start was chosen. So we just mentioned that cars with this number from the random starts would have the 10 repeated systematic sample. So now we are looking at the means of means. So all of the y bar, we can calculate the means of means. So that is about 4.16. And within the y bar, we can look at the variance. That equals to sy bar square. So that is around 0.675 square. So substitute into the formula 5.6, we can estimate the variance of the repeated systematic sampling. So the repeated systematic sampling variance estimator is better than the first estimator using simple random sampling, because we assume in simple random sampling that the population itself doesn't have really ordered trend, so that's only provide the upper bound, or that could usually overestimate the variance. Okay, although we can look at the number of person in the cars doesn't really have a trend itself, because we do not think that the number of person in a car would enter having a trend over the population. So we could also say that they could be quite randomly distributed for that. So using a SRS equation or using a repeated systematic sampling formula to estimate the variance would be more or less similar, unless we suspect there is some trend in the population. Then using the repeated systematic sampling estimates the variance could substantially reduce the variance estimate. Okay. Thirdly, we would use a half sample estimator. So this is just a special case of the repeated systematic sampling that we only choose ns equals to 2. Okay, so if ns equals to 2, then the k pi would equals to 2 times k. So this is called 1 in 2k repeated systematic sampling. So we are using half sample estimator to compare that. So rather than repeated 10 times or 15 times, we simply use repeated twice. So half sample estimator. So that suppose we have even number of observations, so we can divide the population into 2 sets. Then using half sample we would eventually having 2 samples, y1 bar, y2 bar, and we add them up together and divide by 2, and we can obtain the overall y bar using half sample estimator. And the variance estimator would equals to the sy bar square divided by ns. So ns would equals to 2 times, so that would be divided by 2 times. And what we are trying to show is here is a simplified version of the formula 5.7, because we can just use the finite population correction factor multiply to y1 bar minus y2 bar taking square divided by 4. Why is that? Because we can look at the sy bar square, expand these, would indeed come up with the differences between the 2 y bar taking square over 2, right? So if that's the case, substitute into the variance formula, which is sy bar square divided by ns. ns is 2, so 2 times 2, so become 4. All right, so we have a more simplified version of the formula for the estimated variance for the half sampled estimator. Or fourthly, we can use the differences method. Okay, so when we suspect there would be a trend of the population, we usually use a differences method to calculate the estimated variance. And if we see there's a substantial decrease in the variance estimate, we can say that as compared to the SRS variance estimator, and then we can say that we can conclude that there's a particular trend in the population itself. Okay, so in this way, we're using the variance estimate to refer that the population would have some trend. Okay, so how we use the differences method, we will talk about that in a second.